All right, everyone, I'm Mike Wong from Carnegie Science, and I'm going to take you on a journey to look for alien life. So this work is, what I'm going to present today is based on a paper that came out last year in PNAS. Two of us are actually here, myself and Bob Hazen. Bob, raise your hand. So if you want to learn more and you can't find me, come find Bob. So imagine you want to look for life on some alien worlds like maybe Jupiter's moon, Europa. What are you going to do? You're probably going to send a spacecraft there to try to sample the chemistry and look for chemical clues of alien life. One of the best ways of doing this is by using what's called a pyrolysis gas chromatograph mass spectrometer. If you're not familiar with what this instrument is, it's basically a very fancy oven that not only bakes your sample, but tastes it for you too. Real quickly, how it works. You pick up a sample from an interplanetary destination, you flash heat it, which allows the organic molecules, these carbon-rich molecules, to exit the sample, volatilize out, and then get separated by their chemical nature, and then further separated by their masses. So what we are able to do is gather a rich data set of the mass of each of the molecular fragments in that sample versus the time that they come out of the instrument. On the z-axis is the intensity of that signal. If you found something that looked like this on another world, you'd be really excited because this is exactly what the average Earth bacterium looks like to a pyrolysis GCMS. Now, when you're looking for alien life on another world, there's one big catch, which is that that life might not use the exact same biochemistry as life on Earth if it had a different origin and different evolutionary pathway. So it'd be kind of foolish to look for life by saying, oh, I'm just going to identify that particular peak or this particular molecule here. Instead, there may be something more holistic about the distribution of these organic molecules that tells us if that sample was alive or not. So what we've been doing at Carnegie is taking a bunch of diverse organic rich samples, things that are alive like bacteria and plant matter, things that once upon a time were alive but over millions of years, even billions of years, have been degraded into petroleum, shale, coal, etc. And then organic rich materials that were never alive, including what we call carbonaceous chondrites, these organic rich building blocks of planets. And now I hope you can see just by looking at these distributions of organic molecules that they're all very different from one another. And what we can do is we can quantify how similar and different they are from one another and even train a machine learning algorithm on these thousands of different peaks to identify whether or not a sample that it's never seen before is alive or was never alive. And that's exactly what we did. We trained a random forest algorithm on 134 diverse organic rich samples and found that our final model could distinguish something that it's never seen before to a 90% accuracy, distinguishing it from biotic versus abiotic. What's really exciting to me as an astrobiologist is the potential to look for life as we don't know it, right? So in this PCA space here, we have mapped out the distributions of organic molecules in abiotic samples, living samples that were recently alive, and those biotic degraded samples. But if we went to an alien world and we found a sample that plotted here or here in this diagram, we'd be looking at a distribution of organic molecules that's not only markedly different from all known geological samples, but also different in distribution from the organic molecules in life as we know it on Earth. And I think that would be a really exciting discovery to broaden our horizons for what life might be and could be in the universe. So obviously we have really big implications for being able to study life elsewhere, notice it even if it's not exactly like life on Earth, but we also have the potential to impact the paleobiology community and understand in these ancient rock samples from 3 to 4 billion years ago whether or not they contain samples of the earliest life on Earth. This is a project that is ongoing and underway. We are testing a huge number of diversity of new samples in our laboratory. We're hoping to optimize our instrument parameters, optimize machine learning algorithms, and then partner with our friends at NASA and ESA and elsewhere to be able to launch this technique to outer space. So if any of you are interested in helping us, I'd love to hear from you, and let's go find life out in the universe. Thanks.